both the converters, buck as well as boost converter, were having their own limitations. Due to that, they were not capable to operate at maximum power point in all the conditions. So it becomes important to look for another alternative. That the next is in that series is buck boost converter. So if we have the circuit of buck boost converter, then we can have the panel itself, and at power interfacing we are using the buck boost converter. So there will be buck boost converter at the interface unit, and this diode is connected with capacitor that is connected to the load terminal. This is R0, and this unit is buck boost converter. Okay, and at the last turn we have seen that the capacitor was important here in buck converter, though in case of boost converter it was not mandatory, but in case of buck converter it was mandatory to place the capacitor at the input side. So this is the buck boost unit of the system. In this is the terminal voltage between these 2 points. Here this is the switch, so we can say switch, inductance, diode, capacitance, R0, across it the V0, the current that is flowing in I0. Here the current that is flowing here is IT. Here we can say it is IT average, as part of the current will come here, and the current that is flowing from here ICT, we can say IL and IC and so on. Okay, this is the circuit that we can have in case of the solar panel connected to the load through the power interface unit, buck boost converter as power interface unit. And with the control of this switch, we will try to find either it is able to control the maximum to regulate the input impedance of the converter to get the maximum power point. Let us see. So for that purpose we have VL, IL voltage across this. So for that purpose let us divide it into on condition, duty cycle with TS. This is on period, this is off period. Okay, so during when switch is on, the current IT average, it is assumed here IT average, it is IT, the IT current will come and it is in reverse bias. When it is on, it will start charging, so it will be positive polarity, it will be negative, and here will be high potential. And when it is on, in that case it will start discharging, and if it starts discharging then it will be negative polarity. So it will be reverse biased, it will block the current. So the current that is coming from here, IT, will have only one path, that is IL. So the voltage across this will be V input, because there is no drop at all, no another voltage drop. So Vt plus VL will be equal to the 0. So here the voltage across VL will be Vt. So we have this voltage Vt across the VL when switch is on. When the switch is off, then the voltage across this will start discharging, and discharging current will free wheel through this diode, and this current will have two paths. Part of this will go through this capacitor, and part of this will go through this. So this discharging current have free wheel path through this diode, and in that case the voltage across this will be minus V0, because this is discharging. So due to that, it will be negative, it will be positive, and sum of these two will be 0. And from here VL plus V0 will be 0 according to KVL. VL will be minus V0. So in this case it will be minus V0. Okay, and after that the cycle, charging and discharging cycle, will repeat. Similarly, the current from here will be IT, as no another path is there, it is blocked from here. So this will be only current. So IL will be IT, and IL will be, we have seen that the slope will be Vt by L. So it will be with positive slope as it is charging, and for this period the slope will be minus V0 by L. So the slope will be negative. With minus sign, the slope will remain same. So this is IL. At the same time, IT will be, when it is on, IT will have this path. So IT will have same current as IL, though for off period there will be no IT. Okay, so IT. We are not going to have detailed ICT and everyone. Leave it for a while. Just try to find the relationship between input terminal voltage and output voltage, and in terminal current and this current. So for input, in input side, we can have input and output voltage relationship. So from there, this area should be equal to this area, Vt times dTs plus minus V0 times 1 minus d Ts should be equal to 0. From here these two will be cancelled out, and Vt d minus V0 plus V0 d will give you 0. If we simplify this, we can have Vt d is equal to V0 1 minus d, and from here V0 we can have Vt d divided by 1 minus d. So this is the relationship between output voltage and terminal voltage that can be modulated with the duty cycle of the switch. And if similarly we will try to find the relationship between the terminal voltage, terminal current, that is IT average, and I naught, then we have IT average, this can be equal to this current that is flowing from here times D divided by 1 minus D. And if we further simplify, then we can have I naught is equal to IT average 1 minus D divided by D. So the relationship between load current and the average terminal current, we have these two relationships for voltage and current. So if we require to find the relationship between R naught and RT, then divide 1 from 2. For that purpose, we will get this divided by this, Vt D divided by 1 minus D, and full divided by IT average 1 minus D divided by D. And here V output divided by IR, V across the load divided by the current from the load will give you impedance of the load, and voltage across the panel input terminal and divided by this current will give you the input side impedance, that is RT. And if we simplify this, then we can have these two will be outer term, this will be inner term, so it will give us D square divided by 1 minus D square. Further we can have RT D by 1 minus D square. Now with the help of IV characteristics, let us try to understand how with the variation of the D we are able to control the we are able to operate the maximum power point. So let us have IV, this is terminal voltage Vt, and this is the average terminal current IT average. IV characteristics of will be like this, and for time being consider a load line which is operating at this point. This is having load resistance, this is having terminal resistance RT. Corresponding maximum power point PV line will be this is the maximum power point, that is termed as MPP, and the point is PM. As the terminal voltage is required to regulate irrespective of the load resistance, so it should be RT will be equal to the R naught 1 by D divided by D square. And from here, if we will put D is equal to 0, if D is 0, in that case 1 by 0 will be infinite, RT will be infinite, and 1 by RT will be 0. So when D is 0, then the slope of this line, that is 1 by RT, will be equal to the 0. So slope of this line will be 0, means the line will be in this direction. So the point of operation that lies at this characteristic will lie here. So at this point A, D is equal to 0 and 1 by RT. Okay, just write RT. Sorry. RT will be infinite. So slope, that is 1 by RT, will be 0 and line will be here. And for D is equal to 1, so point of operation will be here. And at second case, for example, consider B case, consider D is equal to 1. Once D will be 1, it will be 0 by something, RT will be 0, and the slope, that is 1 by RT, 1 by 0, it will give infinite. So slope of this will be infinite, means line will be vertically placed. So the point of operation that lies at this characteristics will lie here. In case of B, D is equal to 1, RT will be 0, slope will be infinite. So what we can obtain here, with the variation of D value between 0 to 1, we can operate between here to here. So this is the range of operation in the case of buck boost converter that can be possible with the variation of the duty cycle of the switch. So we can operate for full range of the characteristics in this quadrant. Okay, and if we are able to operate at full range, then if load line exists anywhere in this range with slope, any slope, then we can adjust the D to operate at maximum power point. So irrespective of the load resistance, just by adjusting the D, we can get the maximum power point operation in this case. So it was not possible in case of buck as well as boost converter. In the buck converter, we were able to operate in this region if load line was somewhere before this, then in this region was untouched, and if the load line lies somewhat like this according to the load resistance, then it was not possible to operate at maximum power point. The maximum power that can be achieved at that time was this. And if in the boost converter it was possible to operate up to this some point, and if the load line lies this, then in this direction it was not possible to operate. So in both the cases, the full operation was not possible when they were introduced individually between the panel and the load. But when the buck boost converter is used, it is possible to obtain at maximum power point just with the variation of the control of the switching operation of the switch of the buck boost converter.